Welcome everyone to the tutorial for process control analysis, design and assessment. In this tutorial, we will start looking at MIMO system and controller design for MIMO systems. First, we will look at dynamic decoupler design, where we try and pair inputs and outputs in a one-to-one basis, and then control the whole system based on this configuration. So, dynamic decoupler tries to nullify the effect of other inputs on the given input and output pairing. So, in order to do that, we consider the effect of other inputs on this output to be equivalent to some disturbance effect. So, the decoupler is essentially designed to nullify the effect of such other inputs other than the pair which we are pairing the particular output with. So, let us consider a MIMO system where we have two inputs and two outputs. Now, both u1 and u2 will have effect on y1 as well as y2. Because of that, we want to find some linear transformation such that we have variables which are decoupled such that this y1d and y2d are dependent on only the decoupled u's called u1d and u2d. So, now this outer loop can be thought of as a seesaw controller if we were to put a controller here. YD set point and Y1D set point are the set points we choose the system to reach. Based on that, we will compute the error, and the controller will give the corresponding decoupled U. So, we have some decoupler transformation for input and the decoupler transformation for output. By default, we choose output decoupler to be identity, so that we have a notion of the set point as the objective of the variables y1 and y2. But the di will be we will have to choose di such that the effect of u2, for example, on y1 is 0 and the effect of y1 on u2 y2 the effect of u1 on y2 is 0. So, let us take two input two output system where we have g11, g12, g21, g22 as the transfer functions multiplying u1 and u2 for y1 and y2. So, we choose the linear transformation matrix such that it is 1 and d12, d21 and 1. So, how we decouple u1 and u2 is like this. So, u1 u2 equal to di times u1d and u2d. If we were to expand this equation, we will get these two set of equations. Now, you can see u1 of s is u1d of s plus d12 times u2d. Similarly, we have u2. This we can back substitute in these two equations and separate the terms for based on the decoupled input variables u1d and u2d. The dynamic decoupler design works in such a way that the effect of either u1 on y1 or u2 on y2 is made to 0. So, in this case we choose to make the effect of u2 on y1 to be 0. In order for that to become 0, this term has to go to 0. Based on that, we compute d12 as minus g12 divided by g11. Similarly, we have y2 and we eliminate the effect of u1 on y2, and that equation is this, and solving this will lead to d21 of s being minus g21 divided by g22 of s. The important point to note is u1 is u1d of s plus d12 into u2d of s, but y1s is g1 of s plus g11 of s plus g12 of s times d21 of s into u1d. So, this d21 is a function of g21 and g22, and d12 is a function of g11 and g12. Now, we can back substitute and see whether it will decouple properly. So, y of s is g11 times g11 minus g12 into g21 divided by g22 into u1d of s. Now, because we equated this term to 0, this will go to 0. Similarly, we will have y2 of s equals to g22 minus g21 times g12 divided by g11 into u2d of s. Now, so how do we configure and implement such decoupler in Simulink is what we are going to see next. So, here notice that I have given G11, G12 up to G22 as separate individual transfer functions. The transfer function block in Simulink allows CMO system to be specified, but if we were to specify the whole 2 cross 2 system as 2 CMO systems, then we cannot have decoupler effects. So, because of that I have defined all the transfer functions individually, G11 individually, G12 individually, G21 and G22. So, the values are like this. So, we have 3s plus 1 divided by 0.1 s square 1.1 plus 1.1 s plus 1 and 0.8 s plus 1 divided by 0.1 s square plus 1.1 s plus 1 and 3 s plus 1 divided by s square plus 2.5 plus 2.5 s plus 1 and s plus 1 divided by s square plus 2.5 s plus 1, sorry, s plus 1 divided by s square plus 2.5 s plus 1. Now, based on these values we can calculate D11 and D12 and D21 which are given here. Now, the controller PID controller for U1 and U2 will give U1 decoupled and U2 decoupled. The U1 which we are giving it as an input to the system is U1d of s plus D12 times U2d of s. So, we have one term coming from directly from PID controller which is U1d of s, and then there is another term coming from U2d of s which goes into D12 and then added. Notice there is a negative sign in D12 which I have translated to this summation block being subtracted. Both actions will result in same result. The PID controller design I have designed such a way that we will have simple filter along with typical P, I and D values. So, you can see that let us run the system for 100 seconds and then we will see how the system behaves. So, we have given a unit step input to the system. As you can see, there are initial oscillations and there seems to be some offset which is like 0.2 or something, sorry 0.02 or something. Similarly, you have minimal oscillatory variation in the second output and there is some offset which is 0.02. So, this has to be eliminated through proper design of PID controller, and the effect of the model plant mismatch will be more in these cases where we do dynamic decoupling for MIMO systems. Let us look at another method where we use relative gain array to pair the MIMO system such that we will have reasonable control with minimal offset and minimal computation also. So, the idea is pairing is done based on static gains and we can compute the static gain values by final value theorem for given for a given transfer function. So, let us suppose we have done that, then we will have y which consists of y1 and y2 is equal to k11 times u1 plus k12 times u2. Similarly, y2 is k21 times u1 plus k22 times u2. We defined some terminology relative gain as kij divided by kij dash for all I and j values. Now, this kij is the gain of the system, kij dash is the gain of the system where all other transfer functions, all other loops are in closed loop and only the loop in question is in open loop. So, in such case what is the gain of the system is computed as kij dash. Now, we call the term kij by kij dash as Rg, relative gain ij. Again I runs from 1 to n and j runs from 1 to m, they are indices. So, they are only integer. Based on the structure of the matrix K here, this is K matrix. So, based on this structure we can compute relative gain for each and every terminology. So, we will have y1 pairing with u1 and y1 pairing with u2. Similarly, we will have y2 and u1 and y2 and u2. So, we will have 4 terms to calculate. So, if we calculate this each terms and then assemble the number in matrix, we find that we can reduce the whole operation into k1 dot k dot k inverse whole transpose. The dot operator is element wise multiplication. So, we will look at one simulation example, Simulink example, where we use RGA relative gain array based tuning to design the controller. So, as you can see, I have once again configured each and every transfer function individually, and then I have used one PID for controlling each block, but we have to find which type of pairing is the best. So, So, in order to do that, let us see what each final value is, and we will construct the K matrix, and then we will see how each elements how each input has to be paired along with output value. Now, the final value of this transfer function, which is 0.5659 divided by 1 s plus 0.395 is 0.566 divided by 0.395. Let us calculate what it is. K11 equals to 0.5659 divided by 0.395. So, which is 1.4327. Similarly, the second final value of the second system for unit step change is 0.98 divided by 1.351, which is so 0.77254. K12 equals to. The third element is 1.69 divided by 1.351, which is 1.2509, and the final element is 0.984 divided by 3.42. Now, the matrix K is K11, K12, K21 and K22. So, let us compute K dot star inverse of K and transpose. Notice I have used dot star here in order to compute element wise operation, and the transpose is computed when we use the symbol apostrophe. So, we find that the best pairing is the pairing which is contains non-negative close to 1 relative gain. So, here you see the first term which is relating y1 to u1 has negative coefficient, whereas y1 to u2 has positive coefficient. So, we have to pair y1 to u2 and y2 to u1. So, the output of the PID controller is u1 and u2. I have assumed y2 set point to compute u1. So, I have given connections to G11 and G21. Similarly, I have calculated y1, I have used y1 set point and y1 together to compute u2. So, I have given connections to G12 and G22. If the pairing is reverse, this connectivity, that is connecting u1 to corresponding transfer function and u2 to corresponding transfer function will change. The PID I have tuned using simple G desired in direct synthesis method, which is 1 by 0.1 s plus 1, and then I have used the corresponding parameters here, or we can tune it now itself. So, that using trial and error method. So, as you can see, these parameters are not optimal now. So, we can do the tuning here. So, in this case, we have seen that the y2 is getting stabilized here, y1 is still not. So, we will change that operation, or we can as well use the auto tune method, but so now you can see the first output reaches reaches 1 fairly quickly within 8 seconds, whereas there is an offset in the second output. So, we can use direct synthesis method of tuning to compute PID parameters. But since we are not decoupling based in a dynamic sense, we might have to use static gains first in order to compute direct synthesis method based tuning. With this, I will stop this tutorial. We will look at model predictive controller based controller design in the next tutorial. Thank you.